Everybody, I'm going to talk about carbocation stability in this video. So this is really just going to help us figure out like which alkyl halides that we're using can actually be used in SN1 and E1 reactions, where a carbocation is a very important part of the mechanism. So to do that, we really need to be able to identify which carbocations are more stable than others. So here I have a list of the basic carbocations that we have. So this is a primary carbocation, indicated by the fact that we've got one carbon attached to our carbocation. This is secondary, tertiary, allylic, and benzylic. Okay, notice that I don't have my positive charge on any of the pi bonds. They're just next to, right? So as I've drawn them up here, as we get to more substitution, and as we get to carbocations that are next to pi bonds, our stability is going to be going up. Okay. And when you get over here to these three, they're all quite similar, and we'll talk a little bit about distinguishing. But primary carbocations are really bad. Secondary is better than those. Tertiary is much better than secondary. And then these three are going to be fairly similar. Okay. So we're going to see kind of similar reactions happening with them. So there's really two factors that stabilize carbocations, as we can kind of see here. They're kind of split into two sections here. We're talking about like one of these things is not like the other. So the two factors that we're looking at . The first one, if we're looking at these three over here, is substitution. Okay, so substitution is really just a matter of how many carbon-carbon bonds do you have on that positively charged carbon. Okay, so if we think about why that might be, it is an orbital explanation. I'm not expecting anybody to replicate this drawing that I'm about to do, but I'm going to do it just in the hopes that it kind of clarifies like why substitution actually matters here. Okay, so carbocations, as we've talked about before, are planar. They are flat. And coming straight up perpendicular to that plane is our empty p orbital. Okay, so let's go ahead and shade that. So our empty p orbital is what makes it a carbocation. Okay, so if I have, as I've drawn here, this is a tertiary carbocation. So right here, I have a CH bond. Okay, and I also have CH bonds here, right? I'm not going to have those in there though, because it's just going to make my drawing a little bit messier. But I have that CH bond that's right nearby. So what's going on here is I have an empty p orbital. That empty p orbital is desperately wanting electron density, and I happen to have electron density close by. Okay, so in this CH sigma bond, I'm going to switch my shading because otherwise it's going to be, I'm going to obscure my H if I continue. Okay, so in that CH sigma bond, I've got electron density between those two atoms, between my sp3 orbital and my s orbital from my H. So what can actually happen is I can actually donate some of that electron density from that bond to my empty p orbital. Okay, and if I imagine I have a similar situation on the other side, the more of those I have, the more stable that empty p orbital is going to be. Okay, because I've got essentially more electron density being shoved towards it. So the more substitution I have, the better I can make that stabilization effect occur. Okay, so if I just had an H here, I'd only have the two options. But if I have the CH3, then I have all the other ones. Okay, so I can have all of those pushing electron density in the middle towards that empty p orbital. Okay, so that's substitution. So we're looking for more substituents around our carbocation, means more electron density to stabilize that MTP. Okay, and this effect is called hyperconjugation if you want to look it up. It is a pretty cool effect. Try to write it clearly so that you can look it up. Okay, all right, so the second factor is our good old friend resonance. Okay, that's never going to go away. So resonance, as we've already seen since the beginning of the semester, if I have resonance, namely I've got this pi bond that can move over, then I'm sharing that charge between multiple atoms, so I don't have it just localized onto one. Okay, and that's going to be a very, very strong effect. Okay, because as we've talked about, having that delocalization, that's charge spread around, not each carbon has to take such a big load of it. So if we're looking at this, we would normally name that as a primary carbocation. But the fact that it's allylic is so much more important. So it actually gets us more up into the range of a tertiary carbocation. Okay. So then just imagine what other substitution would be like on that allylic carbocation if I have resonance and substitution, right? Those two effects can just kind of bump each other up. Okay, another piece of resonance that is kind of overlooked quite often actually has to do with one of the resonance patterns that we talked about quite a lot. And it's the lone pair next to positive charge. And the reason that that is so important is because, as we see here, this has full octets on every atom. Okay, so that resonance structure is a major resonance contributor. That's going to be a very, very stable carbocation. Okay, because we have those full octets. So let's do one little example here. Okay, so we're just going to rank a few things. So we're going to look at this carbocation. That one. And our final one. Okay, so we should get really quick at this. And we're going to say that one is least stable and 4 is most stable. So we're looking for substitution, we're looking for resonance, okay? So I'm going to name these all off first. So this is a secondary carbocation. This is secondary and allylic. This is primary, and this is tertiary and allylic. So just by naming them, you can pretty much already figure out their rankings. So the primary carbocation is by far the least stable. So that one's going to get a 1. Okay. So next up, I've got 2 secondaries and a tertiary. So if I'm looking at these secondary and secondary allylic, the allylic one is going to have the edge on that secondary carbocation. So that means that this is going to be less stable. So then this is going to be number 2. And then number 3, I have to decide between a secondary allylic and a tertiary allylic. Nothing is going to beat tertiary allylic. Oops. So then I have that. Okay. So this takes some practice, but Hopefully this is something that we can just kind of do visually and just get really good at it. So as always, let me know if you have any questions, and I'll see you all later.